Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Hopefully you guys had a good weekend. Let's actually just jump into it. Yeah, so there we go. That's looking good. Open this up here. Okay, so conceptually, there's nothing new that we're going to talk about today. We're pretty much just going to be going through a bunch of other examples, letting some more people trickling in here. Some more examples, but we're basically going to be doing the same idea. So last time we started section 7.2, trig integrals, and the basic idea is just to use trig identities to help us do integrations. So to compute integrals. So that's what we're going to do. Of course, I'm going to talk about some general best practices when it comes to doing these guys so that you don't end up wasting your time or spinning your wheels or using identities that you don't need to be using and working harder than you have to. And so we're going to talk about now some special structures and methods that go with those structures. And then hopefully towards the end of the class, I don't know how far I'll get into, but we can actually start 7.3, hopefully, where I can just at least introduce the idea of something called a trig substitution. So without further ado, let's actually get to that. So, okay, so here we're in 7.2. The idea is to use trig identities to compute integrals. And we did a few examples. Last time we did the integral of tangent squared. And of course, we just used a trig identity here. Rewrite tangent squared as secant squared x minus 1. And then each of those individually were easy to integrate. Let's say we had to integrate tangent. Similarly, rewrite that as sine over cosine. That is a trig identity, tangent of x equals sine x over cosine x, and that allowed us to use a substitution. So that was that. By the way, that is one of our basic rules, just as we discovered another basic rule last time, the integral of ln x. We did that last time. What was that? What was the integral of ln x?
The integral of ln x was x ln x minus x plus c.
Okay, good. So you should know that by heart. Okay, so at least one person knows that. I didn't see who actually said it, but it's okay. Yeah, now moving on. This is another rule that we should know. The integral of the tangent of x is ln of the absolute value of secant of x plus c, or you can think of it as minus ln of absolute value of cosine of x plus c. These guys are actually the same because of a log rule that allowed us to bring the power up. Then we look at secant. A very strange way to compute secant. You kind of multiplied and divided by this thing that seemed like out of nowhere, and why would anyone even do that? But it turns out to be very convenient. I'll actually show you guys another way that's more constructive to integrate secant, but I need another technique to show you that. But that's how you integrate secant. That is, again, a basic rule that we should know. So what you're going to realize is that, again, step one of doing any integration is to look for whether a basic rule applies. So building up your toolbox of basic rules is very, very important. And we were doing that. Now we're going to actually look at some more special classes of functions. As I mentioned here, and that's again mentioned here in red, we're not going to focus too much on cosecants and cotangents because they behave very similar to secants and tangents. So the idea is if I teach you how to deal with secants and tangents, you'll automatically know how to deal with cosecants and cotangents. So the cotangent is going to behave a lot like the tangent, and the cosecant is going to behave a lot like the secant, at least when it comes to calculus and how you'd manipulate them algebraically. So you really need to only know about secants and tangents for this class. So pretty much if you see anything in the textbook which really kind of focuses on like cotangents or cosecants, except for the absolute basic thing, like you should know that cotangent is cosine over sine, for example. But other than that, to deal with calculus, I'm not really going to ask you much about those. So you can not even worry about those too much. So we are going to look at some very basic ones here. So forms 1 and 2. we're assuming here m and n are integers. And then we're going to look at some more general forms, but we're pretty much going to learn how to integrate things of this form in this section. And that's going to help us, of course, with a lot of future things as well. So let's actually just jump into it. I actually left the notes up on our last lecture for you guys. So I believe some of you guys would have actually tried some of these problems already. So I don't think we will spend a lot of time on this, hopefully. So let's actually jump into it. So the first form, sine to the m of x times cosine to the n of x dx. M and n are integers. There are 4 cases that this guy breaks down into based on whether the integers are even or odd. You're going to see why that makes a difference. So you could have case 1, the power of sine is odd while the power of cosine is even, or case 2, the power of the sine is even while the power of the cosine is odd. These 2 are very similar, by the way. So I'm going to really teach you about case 1 and then just give you an example on case 2. Case 3, both are odd. So you have a sine to an odd power and the cosine has an odd power. And the last case is when both are even, and that's dealt with in a different way. So let's actually just jump into that, case 1. So like I said, conceptually, there's nothing else really to know here. You kind of already know all the pieces that you will need for this section. It's just that now we're just putting them together in a different way, essentially. Okay, so case 1. So remember case 1, this is when the power of sine is odd and the power of cosine is even. So the idea is, and this is a general principle that would apply to case 2 as well, you want to save a factor of the guy with the odd power. So in case 1, so this means that, let me just remind us of that. So this means that you have sine to an odd power and cosine to an even power. Someone else trick them in here. Okay. When you're in this case, the strategy is the following. Save a factor of the odd person, right? So what I mean by save a factor is you'd literally take that factor of sine of x and detach it and move it to the end of the integral. Of course, not behind the dx, but move it to the end, like kind of separate it. And then you're going to change all other sines to cosines using a trig identity, the Pythagorean identity. You know that cosine squared plus sine squared x equals 1. This means that you can change all the remaining sines to cosines using that identity, using the fact that sine squared is equal to 1 minus cosine squared. You're going to substitute u equals cosine of x. You will get something that's very nice, algebraically speaking, and then you just integrate it according to a basic rule. So that's essentially it. So this is essentially integration by substitution. There's a strategy to the substitution, so you know what to substitute. And we have 2 examples here. So let's actually go into them. So A and B, let's move B to the side for now. Okay, so let me do A and you guys can try B. So I realize here that the power of sine is odd while the power of cosine is even. So what I'm going to do is I'm going to save a factor of sine. Still not used to this new tablet. Save a factor of sine. What does that mean? So in my integral, I'm going to take one of the sines and literally put it at the end. So notice I had a sine cubed. I can think of that as a sine squared times a sine. So I save a factor of the sine and I move it to the end, right? The idea is that I'm saving a du. This is ultimately going to be my du that's over here. So that's why I move it off to the side and just save a factor. Now, of course, that's my du, which kind of tells you that I'm going to want my u equals cosine, which means I'm going to have to change all my other sines to cosines.
Professor?
Yes.
So if it were the other way, if it were like sine squared cosine cubed, would technically du then be cosine and then you would want u to be sine?
Yes.
Okay.
In fact, that's a whole other case. So that's actually case 2, quote unquote, that you're
Oh,
mentioning
okay,
here.
yeah, thank you.
But the idea is if one is odd and one is even, you always want to save a factor of the odd one when it comes to sine and cosine. So change all other sines to cosines. So that means here I have a sine squared. I'm simply going to change that sine squared into 1 minus cosine squared. Still have some people trickling in here. And now what we can do is do the substitution. So this is step 3, substitute. So now if my u is equal to cosine of x, my du is going to be minus sine of x. And so that leads us to step 4. We're actually going to do the integration now. So that is going to leave us with 1 minus u squared times u squared times minus du. So this now becomes the integral of, this is going to be u to the 4th minus u squared du. And that's going to be u to the 5th over 5 minus u cubed over 3 plus c. And that's just going to be cosine. Move this to the side. Okay, that guy later. And so that ultimately here is the answer.
Did anything happen to the negative for the negative du?
Oh, I already swapped it. So in the integral, this would be minus 1 plus u to the 4th if you multiply it out. And I turned those minus u squared.
Oh, okay.
You can think of, if I factor out this negative, I would have u squared minus u to the 4th du, and then I just put the negative on the inside. So I already multiplied out the negative, in other words. Any questions on that? Okay, I got the thumbs up, so we're good. All right, so now this example. Maybe make it a little larger. Sine cubed. One thing I want you to notice is note power of cosine is even. How do I know that the power of cosine is even?
Because it's
Is it 0?
Right.
Thanks.
It's 0.
Okay.
0 is an even integer from what you guys know. So technically I can think of this guy as the integral of sine cubed cosine to the 0 to the dx, right? So this is still in this same case. All right, what do we do? Someone tell me what to do here.
So again, you want to take out the sine because it's the odd power. So then you do like sine squared times cosine to the 0 times sine x dx, and then that'll be your du.
Yeah, then?
Then would you change it?
Sine squared x.
How?
1 minus cosine squared x.
Yeah, then?
Then you would make sine x your du, and then you would be negative cosine x, like the last one.
Well, I mean, you'd have
I'm
u
sorry, that's the
equals,
opposite.
u
U would
equals
be
what?
positive cosine.
Yeah. So your du
And
is
then-
going to be negative sign.
Yeah.
So then this would become negative the integral of 1 minus u squared du. Or
Is
in
there
other
a
words,
certain reason you pulled the negative out of that one, whereas you didn't do it with the other one?
no reason. So here we have cosine cubed x over 3 minus cosine squared x over 2 plus c. And that's the answer here. And this case 3,
How did you get the u squared minus u from the set 1 minus u squared?
how did I get what?
How did you get the u squared minus u from the previous step?
This is 1 minus u squared. Oh, that u should actually be a 1. Okay, let me move some things around here.
Professor, can I just ask a quick question?
Yes.
So in the beginning, when you're talking about the power of cosine is 0, why was that relevant to the rest of the problem, or was that just like an understanding thing?
Well, the power of cosine being 0 is what tells us that we're in this case,
Okay, that makes sense.
right? That our
Yeah.
sine is odd and our cosine is even.
Okay, makes sense. Yeah, thank you.
Yeah.
Can we still use this process if the power of cosine is larger than sine, but it's still even?
Yes, you would use exactly this process.
Okay.
So this makes no attempt to measure who's larger here. It's just if the sine is odd and the cosine is even, this is what you do. Okay. Now, to go with what we were mentioning before, so this was a question that came up earlier, but this was the other case, case 2, similar to case 1. Now, case 2 is when it's the other way around, when the power of the sine is even and the power of the cosine is odd, as you see here. And as I mentioned here, it's very similar to case 1. So there's nothing really to talk about, hopefully. Maybe you guys can actually tell me how you want to approach this one.
Would you pull out 1 cosine x, and then you'd have sine squared x cosine to the 4th x, which you would replace with the identity that, yeah.
Okay, how do we change the cosine to the 4th to sines?
Would you need to rewrite it as cosine squared x times cosine squared x? Or is there like some other easier way to do that?
I would do that, but I'd probably write it as that instead. Which is cosine squared times cosine squared, yeah, then?
Rewrite the cosine squared as 1 minus sine squared.
Now?
U equals sine x, du equals cosine x dx.
So our integral becomes u squared times 1 minus u squared squared du. How do we do that integral? So the integral of u squared is u cubed over 3. And we can integrate this by doing something like that, right? Yeah?
Can't we just like multiply it out? Because that looks like you broke a rule.
I broke several rules. Okay, I was seeing who would would disagree with me right now. You were very political. So you didn't tell me like, Jhevon, you're crazy. Yeah, so no, I broke all sorts of rules there, a bunch of rules. So first of all, remember the integral of a product is not the product of the integrals. I can't just integrate the u squared and then try to integrate the second part separately. That's a big no-no. And also, the integral of 1 minus u squared all squared, you can't just kind of do like a reverse chain rule kind of thing, because you need a whole substitution process to go through that. So yeah, you'd actually multiply things out here.
Could you also do integration by parts?
I feel like that would be overkill.
Okay.
I don't know. It's not something that would have occurred to me. So I don't know if you actually tried integration by parts on this, if you could get it to work. Maybe, but it wouldn't be something that would occur to me at this point. Again, there are certain tier levels that you go through, right? So you always think about basic rules first. Can I simplify to apply a basic rule? Will a substitution work before I hit integration by parts? Right here, this integral that I'm looking at, it's a step 2, right? It's something that I can simplify to use a basic rule. There's a power rule hidden in here. So my mind wouldn't even go to integration by parts. You're going too far down in the hierarchy here. So yeah, I would multiply out to get a polynomial, because it's really just a polynomial. It's just right? Just requires a couple steps of algebra. And at this point, it's just a power rule. And our u in this case was the sine. So this is sine cubed x minus 2 sine to the 5th x plus sine to the 7x. And that's the answer. Are we cool? Any questions? Okay, so that's all we need for case 2. Let's see, case 3. So case 3 is if both of them are odd. Let's look at that. So what if you're in the situation where they're both odd, right? So like you have sine raised to an odd power, and then you have cosine raised to an odd power, right? So the idea that we've been working with is you always save a factor of the odd powered guy, then you can use the Pythagorean identity to change the other guy into the guy that you factored off, and then you can continue. What if they're both odd? Well, here's how we deal with that. You save a factor of the trig function with the smaller power. So here's where, there was a question earlier about what if this number is bigger than that? It didn't matter when one was odd and one was even. If one is odd and one is even, you always save the odd one. If they're both odd, now you have a choice. You realize that you can save either one of them, but now how do you choose who you want to save? It turns out you will make your life a little bit easier if you save the smaller one. Okay, so you save a factor of the trig function with the smaller power, then you do change all the other guys, right? Now, that's not to say that saving the guy with the larger power would not have worked. However, you're going to have to work harder, and I'm going to show you with this one example that idea. So let's say you wanted to go with my strategy of saving the smaller power. And then we're going to look at what would have happened if someone decided to save the larger power. So yeah, go. Tell me what to do here. Maybe I'll make this a little bigger.
Professor, when you mean save the smaller power, does that mean like keep it intact and take from the bigger one?
Yeah,
Or the
save
opposite?
means to separate it and put it at the end. So you kind of save it because you know it's going to be your du.
I mean, like, so when you're saying like save the smaller power, like you're choosing that one to separate, or
Yeah,
you're choosing that
save
one
a factor of the smaller power.
Okay,
So in this case, what would that end up being?
so that would be sine squared times cosine at 5x times sine x dx.
Right, so we're going to save a factor of the sine because that's the guy with the smaller power. So the sine cubed, I'm going to think of it as sine squared times sine. And so that's what I mean here by save a factor. Okay. So now once you decide to save the sign, who does that mean we need to change?
Sine squared x.
So now I can change that sine squared x to 1 minus cosine squared x. Which means if I do a substitution, u equals cosine, then this guy is going to end up being negative 1 minus u squared times u to the 5th du. And so that is going to be u to the 7th minus u to the 5th du. That's going to be u to the 8th over 8th minus u to the 6 over 6 plus c. And my u was cosine.
Wouldn't you have to be negative?
Come again?
Sorry.
Yeah, I
Du
pulled
have
out the
to be
negative here.
Okay.
So that's that guy. And the spacing was off, it looks like. So I'm running into the notes from the other sections. So let me move these guys here.
Can you scroll up so we can see the steps for case 3 again?
Yeah, I'm just changing the formatting here. Any other questions so far before we start to move on to other stuff?
What if the powers are the same size?
Pick at random. then it won't matter. Personally, I would probably save a factor of the cosine in that case. Like if it were, you mean like a sine cubed, cosine cubed or something like that?
Yeah.
I'd probably save a factor of the cosine just so that when I do my du, I won't have to worry about a negative sign involved. But honestly, it doesn't actually matter.
Okay, thanks.
However, let's for this particular example, I want to show you what would have happened had I done it the other way. Okay, so going back to this guy. Let's deal with the situation of what if we instead saved cosine. Well, what would have happened then is you would have ended up with something like this: sine cubed x, cosine to the fourth x, cosine x dx. Then you would have to rewrite the cosine and so now with u equals the sine function, that's going to lead us to the integral u cubed times 1 minus u squared du. And what you'll notice about that is, yes, it's doable. However, compared to the guy that we had before, compared to this guy, it's a lot harder, right? So when both are odd, in one sense, you can't really go wrong, but in another sense, the choice you make can cause you to work a lot harder than you need to. So for example, and this is even with that higher powers, like cosine to the fifth. Like if I went cosine to the seventh, then now I'm going to have to expand a cube, a binomial cube, right? Or something like that. Once the larger power gets too large, it starts to get really, really annoying to actually start figuring things out. So it's not that you would go wrong, but the better choice is to actually save a factor of the smaller one. Okay. And where are we here? Case 3. All right, now case 4. Let me find those notes. Here we go, case 4. Case 4, remember when both of those were even, that was our case 4. Now it turns out when everyone involved is even, things get a little bit hairier. You do have to apply an entirely new identity. Again, it's one that you should know, but it's probably been a while since you've had to use it. But from now on, you're going to be using this all the time. It's the double angle formulas. So you are supposed to remember that the sine squared of x, you can write it as 1/2 1 minus cosine 2x. And the cosine squared of x, you can write it as 1/2 1 plus cosine 2x. So these guys come from the addition formula for cosine. So you know that cosine of a plus b is cosine a cosine b minus sine a sine b, which means that cosine of 2a is cosine squared a minus sine squared a. And so in that example, you could realize that cosine of 2x is going to be cosine squared x minus sine squared x. If you solve for the sine squared, you end up with the first equation there that you see in a box. If you solve for the cosine squared, you end up with the second equation that you see in a box there, right? So if everyone has an even power, then the double angle formula is what you're going to use. You're going to change that based on these two identities here. So after that, so the first step is to apply these formulas that I just reminded you of there. So make sure you copy those down and you know them. The second step would be to use, after you apply these formulas and you clean up and simplify a little bit, apply any of the previous methods to finish up. So let's actually see that in action. Let's move these guys over here. Okay, so let's say you have a cosine squared. So you have a cosine squared, it's all by itself. Notice that if the sign isn't present, it means that it has power 0, which means that you have both even powers. Once you have both even powers, your go-to technique, let's make this a little bigger, will be to use the half angle formulas. So in other words, the moment I see like a cosine squared by itself, I would change that to 1/2, 1 plus cosine 2x. And the integral of 1?
X.
X. The integral of cosine 2x?
1/2 sine 2x.
Right. Technically, you do a substitution here, but this is one of the cases where I said you should be able to do the substitution in your head. Once you know the du is going to be a constant, you can just integrate the outer function and divide by the constant. It does not work if the substitution, if the du is not a constant. But yeah, that's going to be it.
I'm
So
sorry,
that,
could you show the formulas one more time, please?
so I'm a little bigger. So yeah, and those formulas, I expect you to have them memorized if you haven't already. Okay. All right. Now, the other example is very similar, so I'm not going to do it. Exercise left for the reader. Let's skip to another one. And actually, let me move this one too here. Okay, some volunteers. So someone can do this one. Someone else start thinking about this one. And let's actually just run through that. Okay, so part C.
So would you do the integral of, well, actually, never mind. You do the integral of 1 minus 1/2 times 1 minus cosine x times 1/2 1 plus cosine x. What would you like?
Right.
Would you multiply the 1/2s together? Okay, yeah, that's what I was gonna say.
So 1 minus 1 plus cosine 2x times 1 minus cosine 2x. Now what?
Is that a perfect?
Would it make sense to like FOIL that out as a difference of squares?
It's a difference of squares. Yeah. So what does it become?
1 minus cosine squared 2x dx.
And in fact, if you wanted to, just realize that that's actually sine squared 2x. How do we deal with sine squared 2x?
Where did the square go from the difference of squares?
What do you mean?
Oh, sorry. Never
Oh,
mind.
it
I
is,
forgot that the one.
yeah,
Yeah,
it's 1
okay,
squared
1
minus
squared,
cosine
right.
squared. Yeah.
Okay,
First, can we do a u sub with u equals 2x and then rewrite the sine squared of that u as the
We
1/2?
could, but u equals 2x is something we can do in our head. We just know we're going to divide by a half when we're done integrating. I probably wouldn't waste time. Technically, it's not wrong, but I wouldn't waste time writing that out. What's the overall concept? Like, I mean, even if you got to the sine squared u, how would you deal with it?
the double
Do
angle
another,
formula.
yeah,
Another double angle formula. So what would that look like?
1/8 times the integral 1 minus cosine 2x.
No.
4x squared.
4x. It's called the double angle formula because you double the angle. Right? So if you
Oh,
apply the
okay.
double angle formula and the angle is 2x, it doubles to 4x. If you apply the double angle formula and the angle is 7x, it'll go to 14x. Right? It doubles whatever the angle is. So the angle now becomes 4x. And so now we know how to deal with that. That's just x minus 1/4 sine 4x. So whenever you have even powers, you're applying double angle formula. So it applied here, here, and then it applied again here. Or maybe I should put it, what am I applying it to? So I applied it to the cosine squared, applied it to the sine squared. So every time I end up with a sine or a cosine with only even powers present, I think double angle formula, and I can keep applying it over and over as often as needed. Once I apply this formula, it doubles the angle, right? It doesn't square the angle, it doubles it. So we end up with that. Okay. Okay, go.
Could you apply the double angle formula?
Mm-hmm.
It'd be 1/4 and then integral of 1 minus cosine 2x squared and 1 minus cosine 2x.
1/4 integral 1 minus cosine 2x.
Squared.
What's squared?
The whole thing.
Yeah, then?
And then 1 minus cosine 2x. Or plus, sorry.
No, something's off.
Would it be 1/8? Because you technically used the double angle formula twice for the sine to the 4th.
Right, it ends up being 1/8.
Oh,
The idea is this sine to the fourth part, it's sine squared, and then I applied the double angle formula on the inside. So the square squares the half and squares this guy. So you get 1/4 from that. And then for the cosine, that's just 1/2 times 1 plus cosine 2x. And then the 1/4 times the 1/2 gives us the 1/8, which is what's right here. Okay, so now we're there. What do we do now?
You can reverse FOIL some of it, I think.
Reverse what?
So you can make it a difference of squares, and then you'll have an extra 1 minus cosine 2x.
Okay, then
Double angle formula again.
applied to.
If I did the cosine squared 2x.
Not so fast. When do we apply double angle formula?
Would you
When we have a
apply-
cosine squared,
No.
Would you make 1 minus cosine squared 2x into sine squared 2x?
Well, that was actually an important question. So let's slow down. Let's think about this. When do we apply the double angle formula? It's very important.
When both the trig functions have even.
When all trig functions have even powers. Now, if we look at this guy here, in this integrand, are all trig functions having even powers?
no.
No, right? Because this guy right here is not an even power. So starting to hit with double angle formula at this point will get you in trouble. So you probably want to do something before doing that. Ideas?
Like Natalie said, can we change the 1 minus cosine squared 2x into just sine squared 2x? Or no, never mind, because that'd be 1. Or I don't know.
You could. That's not illegal. There are actually several ways you could approach this one, but that seems fine. If you do that, what'll happen now?
And you have the rule, sine has an even power and cosine has an odd power.
Not quite. You want to be careful.
You distribute the sine squared.
You first have to
here.
distribute. Now, in this scenario, in the first one, now when everyone is separated by a sum, you can actually look at things separately because the integral will distribute across a sum. So this first part here is in case 4. And this part here is in, I forgot, case 2, maybe is what I called it. Doesn't matter. The point is one of those guys is odd, the other guys is even. So now I can actually apply 2 different techniques at once here. So in the first scenario, what I'm going to do is hit this guy with the double angle formula. That's how we deal with case 4. Then for the case 2, what we would do is substitution. U equals the sine of 2x. My du is going to be 1/2 cosine, not 1/2. It's 1/2 when you divide it out. 2 cosine 2x dx. So it's going to become 1/2 down here. So that would be minus 1/2 times u squared. So in the first one, I can just integrate. And in the second one, I can just integrate. It's a basic rule. So this is u cubed over 3. And so finally, our u was sine 2x. So it's sine cubed 2x. Questions on that? That was brutal. Yeah, I'm easing you guys into it. We start off easy, but eventually you haven't seen anything yet. 2 weeks from now, you'll start to see brutal. So this is why I'm kind of teaching you guys to actually look for these strategies. So I'm taking my time writing out all these strategies here because I definitely want you to be thinking of some strategy in your head when approaching things, because you're going to end up in situations where it's going to be like, I don't know what to do. But if you actually know these strategies and these steps, you'll know the next step every single time. So you'll really start to see the brutal problems as really a bunch of simpler problems. That once I realize, oh, the simple steps to take, my complicated problem is really just a lot of smaller problems. So which steps, Isabella? Case 4 steps? Yeah, so those are the steps for case 4.
So for the part of the integral that was like the cosine 2x sine squared 2x that like fell under case 1 or 2. So you just
right here?
Yeah, so you basically just went through the whole process. You just didn't write it all out, right?
Yeah.
Okay, I just wanted to make sure it was the same thing.
Yeah, so I multiplied out. So at this point, I took the sine squared, multiplied the 1, sine squared, multiplied that. And then I realized I had 2 separate terms where each of these terms had a different strategy that went with them. So the first term was a strategy that applied to case 4. Now, of course, eventually, you're not going to have like in your mind all these strategies. Oh, this is a case 4 subsection 5 paragraph 2. Like you're not, I write it out here now just to get you started. But eventually the idea is if you do a lot of homework problems where you really pay attention to the steps and the cases and you painstakingly make sure that what is my next step? What is the case? Eventually, you'll kind of internalize all of this and you'll kind of know how to do it automatically. But you definitely want to make sure that you don't ingrain bad habits or inefficient practices, because problems will arise where you make one step, even if it's not technically wrong, you're going to end up in a situation where it's just too complicated to actually execute the steps. So it's very important that you first learn the steps and know why we're doing what we're doing. And you should also appreciate that you're starting to see it now. It's going to be even more prevalent in the future. where for a single problem, you might have to apply several different techniques to different parts of the integral. So you really have to know the techniques and really have them ingrained.
On the step at the bottom of the screen, is there a reason you didn't factor out that 1/2? So it was like 1/16, and then both of those integrals, would that be equivalent? Do you have a
You mean
1/2 in
factor
front
out
of
this
both?
half here and this half here?
Yeah, because there's 1/2 in front of each of
Yes,
those.
I could
Okay.
do that. I could.
So for the
So
part,
you could do something like 1/16 times x minus a quarter sine 4x minus sine cubed 2x over 3. Yeah, that's also the same.
so for the part where we have the 1 minus cosine squared 2x, and we change that to sine squared 2x, are
Yes.
we, for the constant or the coefficient at the beginning, how it's supposed to be 1/2, I'm just confused because when you do the double angle, it has a 1/2
Yes.
times 1 minus cosine squared 2x. So are we supposed to take that from outside of the integral from the one?
No, the formula says if I'm changing a cosine squared, I can change it to this. Or if I'm changing a sine squared, I can change it to that. What I want you to realize is what the change that we made here was not a double angle formula. This happened because of this part here is the Pythagorean identity. 1 minus cosine
right.
squared theta is sine squared theta.
Oh, okay. Okay, that
Yeah,
makes
so I didn't apply a
sense.
double angle formula here. I applied a Pythagorean identity.
Okay.
What would happen when in the part that's case 2, because technically the cosine's power is just 1, so would you just like
One
leave
is
it the way
odd.
it is? So
Right.
then you just leave it, you don't like there's nothing to separate, and then you just
Yeah.
substitute.
Yeah, so
the-
technically he's already saved. He's already
Okay.
off to the side. So then I just did the u on the sine, and then that cosine 2x was my du.
Okay.
Okay, so this was case 4. Was that all the examples for case 4? I think so. Okay, let's find the others. Yeah, so that's all the combinations of sine and cosine. Now, at least for integer powers. So I mentioned earlier, I don't know if you missed it, but earlier when I was introducing all the steps, I basically said, for these two cases here, you're kind of expected to pick up on strategies kind of by osmosis, which is not a joke. It turns out that there will be so many situations in these two cases where I can't actually list them all out. There will be an infinite number of varieties. However, by me working through the strategies with these guys, it should give you some idea as to how you would approach a general strategy. So you kind of want to jump in and sort of use those principles. So the basic idea was you wanted to use the identities to change things in such a way that you could save one of the trig functions such that, you know, if you said u equals to the other trig function, that guy that you saved is going to be your du. So that is the overarching general principle that we're trying to apply here. So now let me give you something a little bit more general and try to apply it to this. So let's say this was your guy. So it's not really an integer power situation anymore. Here you are like, it's a cosine cubed and a sine to the minus 1/2, right? So none of the above cases. However, in principle, hopefully after going through those examples, you'll kind of have an idea of what to do here. So you see that on a quiz. What do? Panic. I'm kidding. Not panic. You never panic.
Do you pull out the cosine and make that du?
And then? So you're saving a factor of the cosine. So what do you want to do now?
Change cosine squared into 1 minus sine squared.
And then?
U is sine squared and du is cosine x dx.
U is sine, yeah? Not sine
Yes,
squared.
sine.
So then this integral just becomes 1 minus u squared over the radical of u du. Okay, so how do you deal with that integral? Just integrate the top and integrate the bottom?
Split it into
No.
2 fractions.
No. What? What do you say?
Make it 2 fractions.
Yeah, just divide it. So this is, again, you see a new integral, you go through the strategy all over in your head. Is it a basic rule? Can I simplify it to make it a basic rule? In this case, you can simplify this to make it a basic rule. It's actually u to the minus 1/2, and then u to the 2 minus 1/2, which is 4 over 2, minus 1 over 2, which is 3 over 2. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. And our u was sine of x. Okay, awesome. So now just by following that general principle, you can deal with scenarios that I didn't even tell you about specifically, right? So this is the power of learning these general principles and strategies that I'm going to tell you about. Because I can tell you one of the biggest problems with a class like Calculus 2 is that at the end of the day, you learn so many techniques that the biggest hurdle is just getting started, like knowing what your first step is. And the solution to that idea is to know about principles and strategies that you would apply to things. And so when you end up in a weird situation, you can kind of break it down based on the principles that you've learned before. Yeah, so we have that. Okay, let's see. Now, I think so far we've looked at all the principles for sine and cosine I'm going to teach you. So now we're going to actually move on to things involving secants and tangents. Okay. So let's say now we want to learn how to integrate things that look like secant to the m of x times tangent to the n of x, where m and n are integers. And of course, once I teach you all the strategies for dealing with integers, you can kind of pick up on them and apply them to non-integer thingies. So that's basically what we're going to do. The idea is, again, pretty much the same as was in the case of sines and cosines. There's a trig identity that we have in the back of our mind that we're going to want to use. The obvious identity that connects tangent to secant is going to be 1 plus tangent squared equals secant squared, right? So it means, therefore, you can change a tangent squared into a secant squared minus 1. You can change a secant squared into a tangent squared plus 1. And so this kind of tells you how these two functions will play off of each other, right? So this basically breaks down into 3 cases. And at this point, you're going to start to see things get a little bit more vague, but get used to that feeling. So here, we break this down into 3 cases. So case 1, m is even, namely the power of secant is even, and there's a tangent around, and it's especially useful if the power is greater than or equal to 4, although you can apply this in more situations. Case 2 is if the power of tangent is odd and your secant is visible, right? which means the power of secant doesn't actually matter. As long as you can visibly see a secant there, you can get it to work. And case 3, everything else, right? You can lump everything else into one category, okay? So let's look at case 1, right? So case 1 is when the power of secant is even, right? So case 1, secant has an even and tangent is some other power. And this is especially if greater than or equal to 4. Okay, so here are some scenarios. We can look at something like secant to the 4th. Right? So here, the power of secant is even, it's greater than or equal to 4. The power of tangent is 0. Don't actually really care. So what we would do in this situation, you'll notice, is that we save a factor of secant squared. Why do we save a factor of secant squared? Because we have that identity, 1 plus tangent squared equals secant squared. You can write things in terms of secant squared. It's very convenient for the identity. So first thing to do is I would save a factor of the secant squared. So this is the guy that you're going to save. You don't want to manipulate him. You want to manipulate everybody else. So we're going to change everyone else so that this guy becomes useful as a du. So now, why would secant squared be useful as a du? Well, it relates to tangent in a derivative, doesn't it? The derivative of tangent is secant squared. So it makes sense to actually change all the other secants to tangents. And once the power of secant is even greater than 4, you will be able to do this. You factor off a secant squared, you will be left over with an even power of secant, which you can write in terms of secant squares, which you can then write in terms of tangent squares. So secant squared is actually 1 plus tangent squared. So now I could do something like u equals tangent. Our du be secant squared. So this comes 1 plus u squared du. And that's our answer. Okay, ideas for this one?
So you separate out, you save a secant squared x, then you have secant squared x tan x squared x times secant squared x dx, and then you'll save that for du.
Mm-hmm. Which means, what do we need to do?
You need
So we're
to,
going to save that, right?
I think you need to use the 1 plus tan x in for this secant squared x.
1 plus tan squared. And then?
But then would you substitute in du for secant squared x, u for tan x?
Okay, so that just becomes the integral of u squared plus u to the 4th du. So u cubed over 3 plus u to the 5th over 5 plus c. It's tangent cubed x over 3 plus tangent to the 5th x over 5. Yeah. Case 2 in these guys. So when it comes to secants and tangents, and we're in case 2 basically means power of tangent is odd. And secant present. In this scenario, you save a factor of secant tangent, right? Which is why you need the secant to be present. And then you're going to change all secants. You're going to change all tangents to secants. Let me fit this, fix this format here. You're going to change all tangents to secants using the 1 plus tan squared equals secant squared. Now secant is going to be your u. So for example, so you have here secant x times tangent cubed. You would end up with tangent squared times, you factor off a secant tan. This is the guy that you're going to save to be your du, which means if secant tangent is the du, it means that secant must have been the u, which means we need to change that other tangent to secants. And of course we can do that because we know that tangent squared is secant squared minus 1. And so now I would do u equals secant. My du is going to be secant tan. And so we end up with u squared minus 1 du. And we have that. Another example, more examples, lots of examples. Secant cubed times tangent cubed. So here, the power of tangent is odd. The power of secant doesn't really matter as long as we can actually see it present. And so what we would do here is, again, save a factor of secant tangent. That we want to be our du, which means I need only secants elsewhere, which means I'm going to change this tangent squared into secant squared by going into secant squared minus 1. And then I can do u equals secant. And so this integral will become u squared times u squared minus 1 du. And that's that one. So we can compute that integral. Now I'll just talk about the last case and I'll leave you guys to try some examples for next time. So this was case 2 for secants and tangents. So case 3, you guys are gonna love case 3, it's awesome. This is a case where pretty much you're in any other scenario. And we know exactly how to deal with every other scenario. You guys are going to love this. So let's say we're not in that situation. Let's say the power of secant is not even and the power of tangent is not odd. Now what, right? Let's say we're in a situation where we just have an odd power of secant and there are no tangents, or we have something like even tangents and even secants or something like that, right? Something else, some other scenario. Well, here's how you deal with those. You try something, you hope it works, and then you try something else. And that's the strategy. And I wish I could tell you something actually better than that, but it turns out that that's as good as it gets at this point. It turns out that secants and tangents can get a lot more complicated than cosecants and cotangents, and there is no general strategy for all the other scenarios. And so, like before, like with the last case of the sines and cosines, what you would do in this scenario is just kind of function on basic principles again. Try to save something to try to make sure that, okay, if this was my du, I could make this u, or maybe even integration by parts might come into play. So I guess, I mean, we're a little bit over time already, but I guess what I can do is maybe we can try the one example and I'll leave you guys with these two for next time. So I'll leave these two in the notes, but maybe just to see how you guys are thinking. Let's go with the first example, tangent cubed. Ideas, right? So this doesn't fall in any scenario that we've had earlier, but maybe you can figure out something.
Maybe separate it into tan squared x, tan x dx, and save the tan x dx for du.
Tan would, if tan is the du, what would the u be?
ln secant x. Sorry, ln absolute value of secant x.
Yeah, but do you see that anywhere?
No.
Yeah, so any other ideas?
If you take if you take the tan x as the u, then the du would be secant squared x,
Okay.
which also might not really help us. Can you replace tan squared x with secant squared x minus 1?
That sounds interesting, especially since we know that if we took the tan x as the u, the secant squared is going to be our du. So that might be a promising leap. Now what?
Would distributing the tan x help?
I don't know. We're trying some. Let's see. So tan x times the secant.
Try to,
Hello?
Wouldn't
I don't know, sorry.
Okay.
couldn't we do a u substitution?
Where?
Set u equal to tan x, then du would be secant squared of x.
Okay. So where are you applying the substitution?
Did my mic cut out or?
No. So how are you applying the substitution?
I'd set tan of x for u equal to tan of x, and du would be secant squared of x.
Yes.
So
Where does
then-
that apply?
It would make Oh, to the not the bottommost integral, but the one above that. The
You would apply that substitution here?
yeah. Or I
Yeah,
guess
but you
could
don't
also,
have the secant squared dx. That's what I'm trying to hint at here.
Is this not a case 1 scenario where the secant x is to an even power?
Sure, so you're seeing something, but where? So that's very important.
Could you use secant x tan x dx? And like take that out and leave the secant? Maybe.
Okay, so what I was trying to get at is your substitution wouldn't apply to the entire integral. You're only doing substitution on this part here. Right? Because when you say du is secant squared dx, you have to realize that what you actually have is a secant squared minus 1 dx. The product doesn't work out with your substitution. That minus 1 is messing things up. So what you have to do is you actually have to think of it as two separate integrals, right? So there is the first one, and u equals tan x works here. And then you think of the integral of tan x separately and apply something else there. So when I said, where does that apply? Where does your substitution apply? It only applied to the first term. You have to be aware that your substitution u equals tangent x cannot deal with the entire integral. It actually only deals with the first part. Do you see that? Like why that wouldn't work on the entire integral? Because I mean, if we went here and we said u equals tangent, your du would be secant squared, right? But you don't have secant squared dx. Other than the tangent, you have secant squared minus 1 dx, which is not going to work. Do you see that? Like you don't actually have the du. However, if you were to separate the integrals, then you are going to have that du here. But we have the du on this side. So that tells me this substitution is only going to work for half of this integral. It only works on the first term. So I can deal with the substitution on the first term. On the second part, I have to do something else. So yeah, so for this part here, I can do u equals tangent, and my d is going to be secant squared. So I'm going to have the integral of u du, which of course is going to give me u squared over 2, which is going to give me tangent squared over 2. What about the second part?
That's a rule that we all
That's a
know.
rule. You should know that by heart. What is it?
Ln of the absolute value of secant x plus c.
Yeah. So the moral of the story is sometimes you have to mix and match strategies, and certain strategies you can have an integral where a strategy is only going to work on a part of the integral, and you have to be able to identify it. You have to be so well acquainted with the strategies that you can see when they won't work or when they would work and what part of an integral would it apply to. Sometimes you have to separate an integral to get things to work out.
Was that the rule where it was also okay to write it as the negative ln absolute value of cosine x?
Yes, in which case this would become plus
Plus
ln
ln.
of cosine. Yeah,
Okay, that would be acceptable though.
Yes.
Okay.
So remember, in your tests, a lot of the questions are multiple choice. So what I would say is you can solve it however you want to solve it in the beginning. Just make sure that you know how to convert it. Like if one of the answer choices has the version of the answer with secant, and your answer was the version of the answer with cosine, hopefully you'd be able to recognize that they're actually the same. So we're already over time, so we're going to stop there. Try these two on for size. So these are actually very famous integrals. So sure, if you Google the answer, you will find the solutions to these, but really try to get them on your own. You'll have a great sense of accomplishment by doing this. And it's only hard going through them the first time. If you get through it, you'll be like, "Ugh," in hindsight, it's going to feel obvious. Yeah, should be a lot of fun working through those two. And I guess we will stop there. So I'll post these in the notes when I upload the video at some point tonight, so you'll be able to see these. For now, we shall stop there.
Professor, I don't know if
Yes.
this is a dumb question, but I can't remember, where do you upload the lecture videos, on the website or on?
It's on YouTube.
Sure.
So
Oh, okay.
there is a link to the YouTube. There's a link to the playlist on the website. So if you go
Okay.
to the website, there's a heading that says videos, and you click on that and it links you to the playlist. And then
Okay, and
a
then-
PDF version of the notes is in the video description.
Oh, okay, that was my next question. Thank you.
Thank you.
All right. Take care,
Thank you.
guys. I will see you guys on Thursday. All right. Take care. I'll
Thanks,
see you guys in
Professor.
the next one. Ciao.